In this video, we will cover our second example for exact equations. We have this behemoth looking differential, 2xy over x squared plus y squared dx plus 1 plus y squared minus x squared over x squared plus y squared dy. Now step 1, we ask, could it be exact? Well, first it has to be of the following form, m dx plus n dy equal to 0. Indeed it is, because we recognize our m and we recognize our n. And as long as we have this form, then that says that this differential could lead to a solution of f of x and y set to a constant c, because the derivative of this could lead to this. And step 1, we want to prove that. Is it exact? Well, in order for that, the differential of f with respect to x will have to be m, and the differential of f with respect to y will have to be n. And again, both these will have to be continuous partial derivatives in a region R in the xy plane. And to prove this, these partials will have to equal. So dm dy will have to equal dn dx. So we plug in for m and we plug in for n. And right away we can see that this expression and this expression are both quotients. So taking the derivative will involve using the quotient rule. So where basically it says that the derivative of the quotient equal to the denominator, or low, times the derivative of the numerator, d high, minus high d low over low squared. So we go ahead and do that for the left side. Here we can see that x squared plus y squared is the low. 2x is the derivative of the high with respect to y, so it becomes 2x. 2xy is the high, and this expression, 2x squared plus y squared times 2y, is the derivative of the low with respect to y. And then we have low squared on the bottom. And similarly, we compute the right. Again, we have low squared. We have the derivative of the high with respect to x. So this, negative x squared, it becomes a negative 2x. We subtract the high, y squared minus x squared, and then we take the derivative of the low with respect to x. So we get 2x squared plus y squared times 2x, and then we have low squared. By the way, you may have noticed that I got rid of the 1, but that's because the derivative of 1 is just 0, so it wasn't included in the computation. And now let's simplify this. So the left becomes this, and the right becomes this. On the left side, I was able to pull 1x squared plus y squared out, so it came out and it cancelled. So the 4 dropped to a 3 in the denominator. And same thing on the right side. I was able to pull 1x squared plus y squared out. It came out and it cancelled with the denominator with 1x squared plus y squared, and the power dropped to a 3. Now focusing on the left, if we distribute the 2x and we simplify, we get the following. And on the right, if we distribute the negative 2x, clean this up, and then simplify, we get the following. And both these equalities equal to each other, so our condition is met, and this is indeed exact. Now next, there's two ways we can go about this, so let's do a quick recap of the intro video so we know what exactly we mean here. So far, we have just completed up to this step. We have just proved that it is exact. So from here, there's two ways we can go. We can either do steps 3 to 6, and if that doesn't work out, we can do 7. Meaning we can pick one partial, the simpler partial, and go through this whole process, but if that didn't come out as we had what I wanted, then we could try doing the other partial and repeat this whole process. Or alternatively, we can just skip all these steps and do 8. Now the intuition was this, that if both partials were relatively simple, then all we had to do was integrate. We just had to do the first step, and we didn't have to do all these other steps. The idea was that if you just integrate it, knowing that they were simple, then we would just, f of x, the solution will just be the overlap. But again, this involves that both partials have to be simple. In our case, are they simple? I mean, not quite. We see both of them are kind of a little messy. For example, if you tried integrating this would be kind of a hassle. So it will probably be better to just pick the simple partial m, and then just do steps 3 to 6. So we go ahead and do that. We picked a simpler partial to integrate it. We said that the simpler partial was m, and it was set to dx. Integrating this with respect to x, we shall get the following. Again, the integration constant was g of y with respect to y, because the integration constant is always with respect to the other variable. For example, we integrated with respect to x, so the integration constant is with respect to y, the other variable. Plugging in for m, we get the following. Now this integral is also a quotient, so we will have to apply a u substitution. Now, it may be a little daunting because we see not one variable, but we see two variables, x and y. So you may wonder, how do we do this? Well, the idea is still the same. Think of it like this. Since we're integrating with respect to just x, you want to treat the y as constants. One way to reframe this is to rewrite it as such, where I let y equal k1 and I let y squared equals k2, both of them being constants. So we let u equal k2 plus x squared. That means du equals 2x dx. Notice how the k2 went away because it was a constant. And then we let du over 2 equals x dx. And then plugging in for u, and then plugging in for x dx, we shall get the following. Now integrating this, we shall get this. Plugging back in for u and our constant k1 and the other constant k2, our solution is this. We cancel the 2's, we plug back in, and get the following. Now step 4 is to differentiate with respect to the other variable to get the other partial. The other variable being y, so we differentiate with respect to that. And this shall give us n, because df dy equals n. Now, how do we solve this expression? Well, we solve this integral right here. It came out to this. So this whole expression is just this and the derivative of that with respect to y. And it will involve doing the quotient rule because we have a quotient. So the solution comes out to the following. I'll let you work through that. Recognizing that 2y squared minus y squared simplifies to a single y squared, our expression becomes this. And then we also have g prime of y in short. Step 5 is to isolate the integration constant and integrate it. So we isolate for g prime of y. And in short, rewriting everything, it's just n minus the integral m dx and the derivative of that with respect to y. And plugging everything in, we shall get the following. Where this was n, and this was what we just solved here. These cancel, so essentially we are left with just 1, but the integral of that with respect to y is just y. Now step 6 is to substitute the integration constant and simplify. So we want to substitute for g of y back into this, and we get this. And this pretty much is our solution, so we set it to a constant c, and we have our answer. Now one way to verify this is to take the derivative with respect to x and then derivative with respect to y and see if they equal m and n respectively. So we do the first one. Plugging in for f, we get the following. This right here is again a quotient rule, so it comes out to this. I'll let you work that out. The 0 cancels the stuff on the left, and indeed we see that this is equal to m, because the negatives cancel each other. So we have verified our first. Now let's verify our second. Plugging in for f, we get the following. This again is a quotient rule for the second term, y over x squared plus y squared, so it works out as follows. Again, I'll let you go through that. Simplifying this, this becomes this. And we see that this is indeed equal to n, so we have verified our second. And this completes our example.